Okay, hello everyone. Let's start our session. Today, we are going to continue our discussion on a frequency domain analysis and how we can model the system in frequency domain. Before, in the previous session, we talked about the Laplace transform and why we use it, what are the characteristics of the Laplace transform, what is the definition. We saw some example of how to actually use Laplace transform to basically change the linear time variant equations, mostly like differential integral equations, into the Laplace form. So it would be easier for us to analyze the mathematical kind of like derivation and drive the mathematical kind of like derivation and analyze the system. Now, we are gonna in this session today, we are gonna talk about why we learn actually that Laplace transform and how we can use it in order to model a system. Okay. So far, we treat the Laplace transform as just a mathematical tool. Okay, now we are gonna go to the application. Now, there is a concept named transfer function in system analysis, which is defined as the Laplace transform of the impulse response. These are important terminology, or these are important point. The Laplace transform, come on. Oh, no. The Laplace transform of the impulse response where the initial condition are zero. Okay? And it represents the system. Now, what that means? That means when we wanted to like model the system, we are gonna consider that all the initial values, either like it could be like f of f at time of zero, or the derivative of the f at time of zero, or like a second derivative or nth derivative of that f in zero. All of them are the value of all of them is zero. Okay, so this is the first kind of like condition and assumption that we are going to take when we want to like define the transfer function. Another part is that if you remember in our equations in previous session, we always have a ut, like a step response, or kind of like another kind of like functions of that ut as our basically input value. Okay. Now, when we want to like consider the transfer function, we will consider that ut as the impulse function, which is basically the delta Dirac. Okay, and we know that the delta Dirac function is gonna be the transfer function. That the Laplace transform of a delta is gonna be 1. Okay, so we basically eliminate that force from our mathematical model. So everything now depends on basically the actual function of the input. Okay, so there is no step multiplying by that input. Okay, and what's happening in our system. Okay, now you already remember that we normally use a differential integral equation, and since we can get rid of the integral by basically differentiate the whole formula, we have a certain order of differential equation that explain to us how the system will govern. Okay, and what is the relation of the output that we want versus the input that we have. Okay, now we already learned about the characteristics of the Laplace transform, and we know how to transfer that crazy differential equation into a very simple algebraic Laplace equation. Okay, and we know, okay, if we have like an nth derivative of a certain function, we can simply replace it by s times n of that function. Okay, sorry, fs to the power of n times that function, the Laplace transform of that function. Is that good? Yeah, go ahead.
Is this still chapter 2?
This is chapter 2. Yeah, we are still on the frequency domain methods. Okay, now basically in the previous session we learned about the mathematical definition of a Laplace transform. Now we are going to use it to analyze and model the system. Okay, so if we have this differential equation, we can turn it to the Laplace equation, to the frequency domain equation. Okay, using the Laplace transform, and simply replace all the derivative with their equivalent in a Laplace, in the S domain. Okay, now here, when I derive the Laplace transform of that differential equation, I already factor out that CS here, CT is the Laplace of that is going to be CS, C of S. So I just factorize the C and R. The rest is the same Laplace transform of that differential equation. Now that we have this Laplace transform, okay, that S domain formula, now we can define the relation between the output and the input. That relation, CS over RS, we call it transfer function. Normally we show it by a capital letter G. Okay, but it doesn't matter. Like this is like a kind of like the agreed upon kind of like setting for showing the transfer function. Normally it shows by GS, or if you have two transfer functions, the next one is going to be H of S. Okay, so this is kind of like the idea. Now, when we define the GS, it basically means that we can represent any type of the system that we have as a block diagram. That we inject an input into that block diagram, which is in this form R of S, and the system would do its work, that we model that work using this transfer function. Here you can see that, and it would give us the output, which is the C of S. Are we good on the definition of the transfer function? Now let's actually do an example. Okay, it's pretty simple. The definition is pretty simple. You just need to like work and like practice to get fluent in how to find a transfer function of any type of system. Now, this is if we consider that we have a system that this differential equation d of ct over dt plus 2ct equal to RT would drive our system. This is the governing equation of our system. What we have to do to find the transfer function is step one, get a Laplace transform of that equation. So we know the differential is going to be S times whatever function we have. Okay, plus this is not going to, well, this is a coefficient, so it's not going to change anything. So it's going to be 2C of S, the Laplace transform of this function. Okay, and R is also going to be the same, because we don't change anything, we don't do any operation on R. Now, since we have the algebraic equation in the S domain that defines what is the relation between the output and input, now we can find the transfer function, which is the output over input, and simply is going to be a 1 over, what is that? 1 over S plus 2. This is just a like algebraic kind of like derivation. It's very simple. Is that, we are good? Is that clear? Now, let's try another one. Let's say we have the transfer function of a system. In this example, you are going to see why actually we developed the transfer function. Okay, we have a transfer function of the system. Okay, And we are going to define that RT as a step function. Okay, so basically in transfer function, that step function is multiplied by that delta zero. Okay, now we know that the Laplace transform of that step function is 1 over s. So what would be the output when the r is 1 over s? What would be the c? It's simply that transfer function times rs. Are we good? Is that clear? No. So if the transfer function, if the output is the r times the transfer function, that means for in this example, our output Laplace equation is going to be 1 over s times s plus 2. Okay. Now, since we have the output of our system, now we can actually see what would happen in a time domain. Okay, by taking an inverse Laplace from that output. So you see, when you have a transfer function and you know your input, that transfer function times that input, which gives you actually the response of your system. And you can simply take it back, transform it back to the time domain, and see actually what's going to happen in your system, like what type of waveform you are going to see in your oscilloscope, for example. Okay, now we know how to kind of like separate the two terms in the denominator. Okay, we already talked about that, and you already learned probably in like a mathematical course that you passed. So basically, if we separate these two terms, our CS is going to be like this. Are we good? Now, since the Laplace transform is linear, the characteristic of the linearity characteristic of the Laplace transform would help us to actually turn back the CS into the time domain by simply getting the Laplace inverse of each of these two terms and add it together. Or in this case, subtract. Okay, so if we do that, we are going to find that this 1 over 2 times s is going to be Laplace inverse is going to be 1 over 2. And this one is going to be minus 1 over 2 e to the power of minus 2t. So now this is the function that you are going to see if you have like a circuit that this is the transfer function and you input and a step kind of like input, step voltage as an input. Okay. And this is going to be what you are going to see at the output of your system.
How come like this class you feel this like in other classes? Like wow.
Doesn't matter. It's kind of like a definition. Okay, like for example, when we want to like analyze a circuit, is normally either current is our output, or voltage is our output, or power is our output. So we just use the same kind of like parameters, the same letter that we use, like is going to be V of S or I of S or P of S based on the parameter. Okay, so it's just a random learning naming. So this one is normally named G of S or H of S, but the rest is based on your own kind of like choice. Now, let's go a little bit complicated. Now here we have a second order differential equation. Okay, how we can find the transfer function of such a system. Now, we already know that when we have, for example, a second order differential, the Laplace transform of that would be, you remember, s to the power of 3 c of s, please work with me, c of s, okay? This is not good. Work with me. S, C, come on. of S minus S squared, the initial value, minus S times the initial value of first derivative, okay, minus the initial value of second derivative. That was the Laplace transform of this third order differential operator. Are we good? Now, remember, what was the assumption in transfer function? That all the initial values are 0. So all these terms, what happened? All these terms are going to be eliminated. So we only have S to the power of 3 times C of S. Same goes for the second order and first order derivative, and same here. Okay? Are we good? So now we have a transfer function that says the Laplace transform of this, based on the Laplace transform of this equation, that says that S to the power of 3 plus 3 times S squared plus 7 times S, sorry for the, I can see what I'm writing, so it is going to be difficult to, plus 5 times C of S is equal to S squared plus 4S plus 3 times R of S. I'm writing is just take a lot of time to, right. Okay, now we have our Laplace form, S domain form of that differential equation. So transfer function we said is going to be CS over RS. So it's a simple algebraic kind of like derivation. Okay, so the transfer function is going to be, as you can see, S squared, I'm on. S squared plus 4S plus 3, that the multiplication of the RS, divided by the whatever we have as a multiplication as the multiplication of the CS. Are we good? So this is basically how we transfer a differential equation to the S domain, and we are going to find the transfer function based on that. Everything clear? Okay. Now we have another. Let's go like back. We have the transfer function, which is a higher order. It's not just the first order, and we wanted to like turn it to the time domain. Again, it's very simple. GS is CS over RS. Please do not change. Okay. So basically CS times the denominator is equal to RS times the denominator. Very good. And if you take the Laplace inverse of that equation, we know that the S2 is simply the second order derivative. S is first order derivative. Same goes for the denominator. So we have our differential equation that we find from the transfer function that relates basically the output and input. Are we good? Any question so far? No? Okay. Now, when we talk about the electrical system, it doesn't matter what part the system is, what type of component is. We already know that. We already learned that in circuit analysis. We can run an equivalent circuit that represent that original circuit by only using R, L, and C. These are the main components. So you might have like an op amp, but you already know like the model of op amp is like input impedance, depending voltage, a dependence voltage, and an output impedance. Okay, so you can simply model that a specific component using these three passive components. So we have to learn how to deal with these three component, and then we are good for analyzing any type of electrical system. Okay, now let's move on. First component is capacitor. We already know that if we consider voltage and current as an input and output, okay, we can relate these two components by the differential integral equations that we know from the circuit one. Okay, so the voltage across the capacitor through time, okay, is a time variant function. Okay, is going to be 1 over c, the integral of the current. So if you know that, that means the current is going to be c, derivative of the voltage. Good? Now that we know these two functions, what would be the voltage divided by the current? It's going to be simply 1 over s CS. This is kind of like the concept of the impedance. Is that clear? Are we good? And the admittance is going to be CS. So it's reversed, like the current versus, so current is output, voltage is input. Are we good? Are you familiar with the impedance and admittance? Yes? Okay. Now, same goes for the resistor. Resistor is simpler because it has a linear kind of like relation. In a resistor, the current and voltage have a linear relation. Okay, so simply the voltage is Ri and the current is 1 over R times V. Okay, so the impedance in the S domain is going to be R, that coefficient. Okay, and the admittance is going to be 1 over R, which we normally show it as G in the circuit. Either one of these would help you to like run the analysis. Okay, so you don't need to like focus on what is the impedance and admittance. Now, for the inductor, again, we have the voltage is equal to L, the derivative of the current, and the current is 1 over L, the integral of the voltage. So using that, we can find that the impedance of an inductor, which is the S domain representation of that relation between the voltage and current, is going to be Ls. Okay, and the admittance is going to be 1 over Ls. Now you know that in the circuit analysis as like that J omega L, and for capacitance is 1 over J omega C. Okay, and we talked about that. This is because we consider S equal to J omega when we have like a sinusoidal input, which is just alternation without any damping, it's a constant alternation. So we don't have like a DC or like damping. Very good. Is that clear? Now that we know how we can represent each of these components in an S domain using the impedance, the concept of impedance, now we can start actually analyzing an actual circuit and find a transfer function. Okay, now, for example, in this circuit, we want to find V of C over a relation of the V of C to the current. So V of the voltage across capacitor is going to be our output. Okay, and our input is the current that we have. Now we know that if we run a KVL, the L dit plus Ri plus 1 over C, the integral of the current, is going to be equal to our voltage source. That should be fully clear. Is that okay? Very good. Now, we simplify basically that derivation. Why we do that? Because we wanted to like get rid of this integral. We take another different derivation. Okay. And now we have a second order differential equation that relates the input and output. Okay. Now, this is QT is C times VC is the charge. Okay. We replace the current by charge. It's simplified equation. Okay. Now that we have this, let's kind of like simplify it a little more. We multiply everything here by C. Yeah.
I think I meant this previous slide. So we took the another like derivative to get rid of the integral.
Yeah.
But by taking the derivative, we're getting Q of t, like the derivative of I is the Q of t.
Not the, yes, the derivative of the IT. What is I? I is the average of moving charges.
Okay.
Is that correct? Yeah. Now, what is the derivative of the moving current? The charges.
Q
Makes sense?
Charge.
Yeah. So it's basically, consider that. I wanted to be fully clear. Q are the charges. If you average them out, all the moving charges, if you average them out, you have the current. What is the averaging? We talked about that in previous session. Is the integral. So if the integral of the Q is I, the derivative of the I is Q. Make sense? Okay. Now we have our equation. We simply here we multiply everything in a left-hand side of equation by C to get rid of this C in the denominator. It's going to be easier. So now we have a very simple differential equation, second order differential equation. We run the Laplace transform over our equation. Okay. That should be already clear for you because we already solved that in previous examples. Now that we have the Laplace transform of the both side of our equation, we can find the voltage. Sorry, the input was the our source. The voltage across capacitor as output based on the input, which is our voltage. Are we good? So this is going to be the transfer function of, for example, this one loop circuit, one RLC loop circuit. Any question? No? No? We already talked about the kind of like the model of each of the component in S domain, and we called it impedance. I want to kind of like emphasize that and basically say that it's the Laplace transform that describe the voltage current relation of each component, assuming, remember, zero initial condition, okay, is going to be called impedance. So this is the definition of the impedance, if you want. Now, I want to encourage you to search on that and find the kind of like the physical definition, the physical intuition of what is impedance. Because in this definition, we only define it from the mathematical perspective. Okay, let's search on that and find out what is the intuition over the impedance when you look at it from the physics perspective. I really encourage you to do that. It gives you a very good understanding of circuit analysis. Now, let's do a little more complicated city. We have the input, which is our voltage source, and we want to, again, find a transfer function that relates the output voltage across the capacitor to that input. Okay, now we have two loops. Again, it should be easy. It's just a KVL, KCL derivation over that circuit. So if we do that, we would find our system, but the simplest way to do the system analysis, because we already are familiar with the concept of impedance, is to simply transfer our circuit to the S domain. instead of dealing with those differential integral equation. So by transferring that, R is going to be the same. Resistance, we already know, is the same in time domain and S domain. Inductor L is going to be Ls, and the capacitor C is going to be 1 over Cs. Are we good? We simply transfer our circuit to the S domain. In previous example, we run the analysis in time domain, and then after we find the equation, we use the Laplace. Now here, at the first step, we are using Laplace to transfer the circuit to the S domain. Very good. Now, 1 kVL is going to give us R times the current, the first current, plus, this is kVL, Ls times that current, okay, minus, this is a KCL again here, okay, so this current in L, if you run a KCL here, is going to be I1 minus I2. Is that clear? This is KCL on V1, okay? Is it VI? Yeah, VI. Now, this is going to be the KVL in our first loop. And we know how to run a KVL again in our second loop. Is that clear? Any question about those KVL equation? Are we good on that? Now we have two equations that relates the input voltage, okay, to the current. How we can show that? We have a set of equation. We are going to use matrix for. So we have a vector of our current. Are we good? This is the vector of the current. We have a vector of input. First equation is Vs, second one is 0. We don't have any source here. Are we good? And what's relate them? What's relate them is the coefficients that we have here. So we know that, okay, if we wanted to like run the equation, I1 times R1 plus Ls minus Ls times I2, this is the matrix multiplication. Okay, is going to be Vs. So we have that. What is the equation? This is a multiplication. Sorry. This is a multiplication. Okay, is going to be the matrix representation of the 2 KVL that we have. Very good. So what is going to be the GS? Is going to be vector I. Okay, we defined, we are going to see that why. We define I2 over Vs, because if we want a VCT, we simply can work it out. Okay, so in this equation, if we find I2 over Vs, it simply means that we have Ls squared. If you do the inverse of this matrix, you know how to do the inverse, right? Inverse of the matrix, right? Search on that. We are gonna solve some example later on because I don't want to like spend so much time on each of example. So here we basically run an inverse in this matrix, okay? And based on that, by simplification, we have LCS square over that denominator that we have. This CS square, so sorry, the CS in the nominator is actually the denominator of this delta. It just went up mathematically, okay? Is that clear? No. So now we have our GS. Now, if you wanted to like have the VC as the output, what you should do? What you should do here, the transfer function describes I2 over V. So the output is the current passing through the capacitor. If you want to have the voltage across the capacitor as output, what you should do? Sorry?
Now I was saying like move the voltage to the side.
No. Here, this equation, that G, come on, G of S is I2 of S over the voltage source that we have. Okay? Now, I want you to find H of S, which is the voltage of the current in S domain over that input voltage. If you want to find this one out of this one, what you should do?
Inverse is a matrix, right?
If you do the inverse, it's become Vs over I2.
So we're looking for HFS.
We're looking for the voltage across capacitor against the source that we have. Anyone? What are you changing between GS and HS? What are you changing? We are replacing the current with the voltage. The current of capacitor with the voltage of the capacitor. Are we good? Is that clear for everyone? I2 is the current passing through the capacitor. Between G and S, we're replacing the current with the voltage for the capacitor. Are we good? Any question about that? Is that clear?
Why do we define HFS?
I'm asking you. Like, I demand to find the H of S, like, for example. Or, for example, you have the transfer function for the characteristics of the system that relates the current to the voltage source. But, for example, for any type of reason, in your circuit, you want to see, okay, what's going to happen in the voltage of the capacitor. Now, let me give you an example. When you work with a capacitor in industry, okay, one of the most important aspects of the capacitor is transient voltage. Okay, so when you switch or any type of like kind of like a transient activity that happened in your circuit, okay, it would create a voltage surge, which is a very short, high voltage peak added to the voltage, the steady state voltage of your capacitor, which actually the height of that surge is going to be significantly higher than the nominal voltage that you're working. Now, the capacitor, the actual capacitor that you're going to work, especially the electrolyte capacitor, they have a certain tolerance. If you pass the tolerance, it will explode. So you need to know what you're doing. It's not just the current. That by current, you know if you in a steady state, you are using the capacitor in a proper range. By analyzing the voltage across the capacitor, you're finding that if that what you're doing with the circuit would also make the capacitor characteristic to remain in the safe interval regarding the voltage. Now, this is the reason I wanted to like give you one reason of why you need to both analyze the current and voltage of the capacitor, but that's not for this question. Okay, in this question, we find the transfer function of current passing through the capacitor versus the voltage source that we have. Now, for any type of reason, we wanted to actually again find the voltage, the transfer function between the voltage again across the capacitor versus the source that we have. Okay, so these two equations tell you what's going to happen if you have such an input. The first one would tell you what's going to happen to the current. The H1 would tell you what's going to happen to the voltage for the capacitor. Now, how you can find the H out of G? I already gave you the hint. What we are doing, the difference between the two is that to move from G to H, we replace the current of the capacitor with the voltage of the capacitor. If you want to do that, what you should do to the rest of the equation?
Keep the denominator, but the numerator changes. But we have to do
How?
KCL, KVL to find, so we found LC S squared is the current across the capacitor. So do we do some kind of Ohm's law trick now?
What is the Ohm law?
Well, V equals I times R, but in this case, we're using an impedance. So it'd be like, what, V equals I times Z, right? And,
So what is this V?
I is, what is? I is
This
that'd be,
V across C, your answer is correct. Okay, but you need to practice. When you see that, you have to instantly think of the answer. Okay, V of C is, we said, as your friend said, the impedance of the C times the current of the C. Okay, what is the impedance of the C? 1 over CS. Correct? So here, this H of S is 1 over CS times I2 VS. Correct? Which is 1 over CS times G of S. Make sense? Is that clear what we did here? Now, you might have several other kind of transformation that we did. I want you to think of it. That's why I ask you to learn the physics perspective of the impedance. Okay, this is just a mathematical perspective. So if you learn that understanding, if you get that understanding, okay, that now that easily you can transfer from the variable to variable in estimate. Are we good? Okay, now using this kind of trick, you also can find like the parameters of L versus the input. You know, it's just using the concept of impedance and what is the relation of these input output. Good? Oh, okay. This is kind of like the next example. Yeah, go on.
Sorry, can you go back to the previous slide? So we just turned the transform the circuit into from time domain into S domain. Then we found the total voltage from there. We were able to find the transfer function, GS.
Yes.
So GS describes the just the current coming through the capacitor with respect to the input, like voltage.
Yes.
Okay.
The voltage source.
And then we found the voltage by like multiplying by 1 over CS to find the voltage of the capacitor with respect to the voltage source.
Yes, it's only using the Ohm law. So if you wanted to like find the transfer function that describe the relation between the voltage across the capacitor to that input that you have, okay, instead of the current of the capacitor, voltage of the capacitor.
Okay.
You can simply so since you have already the transfer function that relates the current to the input, you simply can use the
So this is just
Ohm
showing
law.
that, like you
Yeah.
can easily find your voltage based on
yes.
for
Yes. Now, next example is the hard way to find that. Okay. Now, you want the voltage across capacitor over Vs. The hard way is to run all the KVL, KCL again. Good. So if you run that, you see, we have the CS. Now, these are because we use the admittance. So it's 1 over whatever we had before. Okay. So don't get confused about that G1, G2. Okay, it's just the admittance of whatever we had as an impedance. So, what is that? Let me go back to see if. Okay, that's the same question. Now let's move on to more complicated kind of like circuit that play a lot. Okay, I already told you that you can equivalent any type of component with RLC. Now, I am gonna in this equation, in this example, I'm not gonna use that equivalency, and I'm directly analyzing an op-amp circuit. Okay, which this one, anyone knows what is this op-amp circuit? Do you remember what we have here? It's actually inverting, but what is the actual that not just this amplifier, the whole circuit? What is that? Anyone know? It's not related to our discussion. I just wanted to like have a little fun, you know. What is this? What is this?
Is it a filter?
Is it a filter? Yeah, it's a high pass filter. Correct?
Yeah.
Now, what is this part? Now I'm gonna no. It's a type of direct application of the op-amp, which is integrator. Whatever you have here, it would integrate it and give you the output. Okay, this is integrator. Now you're gonna learn that. Do you pass ELAB? Any of you? Yeah, you should work with that integrator in the ELAB. Okay, so now let's move on to this part. Now we want to find the transfer function of this circuit, which is the output versus input. Okay, output of the circuit versus input of the circuit. Now, using the amplifier, we simply know that this one is the output is A, the gain of the amplifier, times the difference between the two terminals. Are we good? V2 is the non-inverting one. Let me write that down. That one we should be pretty good with that. Yeah, this is the equation of the amplifier. Are we good? Now, the impedance Z1, if you run the equation, the impedance Z1, which is, come on, this one, it's a parallel of two impedance. You already know how to find the parallel impedance. I hope so, actually. Okay, so this is 1 over CS, this is R. Okay, so the impedance is 1 over CS plus R, which if you do the derivation is gonna be 1 over CS plus 1 over R. Are we good? It's just turning these two in a one equivalent impedance. This we have two parallel impedance. Now, what about Z2? This one. This one, we have R2 and CS in parallel, in series. So the impedance of the whole thing is going to be R2 plus 1 over CS, C2S. Are we good? It's just the series of these two, and this one is the parallel of these two. Okay, now we have the Z1 and Z2. Now look at this. V2 is 0. It's grounded. Correct? What is the characteristic of the op-amp from the input? It has high impedance. What that means? That means there is relatively no current, approximately no current passing between the two input, between the inverting and non-inverting input. That means there is no voltage drop against that input impedance. So whatever voltage you have here, you have here. Are we good? So this one doesn't drain any current. Current here is 0. Meaning whatever current is passing here is going to go through this Z2 impedance to the output. Now you have simple KVL. Make sense? You have simple KVL. This is V2. Okay, so VO here is gonna be connected to here. You have a voltage. Here also you have a voltage terminal, AB. Are we good? You run the KVL. If you run the KVL, you simply have two series impedance. You know how to do that. And you know how to relate the current and the voltage. So simple KVL gives you the relation between the output and input. Is that clear? I don't want to go to the circuit analysis concepts. I want to make sure that you know what I did. Any question? No? So we're good. Same kind of like stuff going here. You have way more complicated system. Okay, when I say practice, that means you have to, when you look at this, okay, the expectation as an engineer is that, okay, I look at this, I have to instantly know how to find the transfer function. So again, very easy. You have two parallel impedance here, one one series impedance here, and you know these two voltages are equal to each other. Okay, because it doesn't drain any current because of that high impedance, ideally infinity. Okay, so if this is VI, that means here is also VI. Makes sense? Now, look at this. We have VO here. We have, let's say it is Z1, this is Z2. We have Z1 here connected to the Z2. Come on. Z2 connected to the ground. And this is VI. What is that? As from circuit perspective, circuit analysis. When you have such a circuit, you have to instantly remember one specific circuit when you see that a specific circuit. What is that? Anyone?
Voltage divider.
Voltage divider. So the VI is going to be Z2 over the summation of the Z times VO. Make sense? So now you have the relation between the two, between the output and input. Solve. You know what I'm saying? So if you practice, is this crazy circuit is actually can be analyzed and modeled within a minute. Are we good? Now, we're not always dealing with the electrical circuit. We know we have motors, we have like either rotational or linear motors or any type of kind of like actuators that we have in our system that works that works alongside of electrical circuit. As a true engineer, if you only know how to analyze the electrical circuit, basically you're halfway done. You need to know how to analyze the whole kind of like situation, the whole system. So it's better to get familiar with the mechanical part too. Now, for the mechanical part, I don't want to go through the mechanical engineering concept, okay? And to be honest, I'm not fluent on that. I just know what's going on, okay, generally. Now, either we have in our system, we have a spring, a damper, or a mass. These are, again, like RLC, the three components that we can use to create an equivalent mechanical kind of like, I don't want to say circuit, but mechanical kind of like system out of any complicated original system. Now, what happened? Why is that? Now, the relation, the impedance please pay attention to what I'm talking about. In mechanical engineering, they don't have the concept of impedance. I'm using on a purpose here. Okay, the impedance of a spring is K, like a resistor. The impedance of that damper, is like a L, is Fs. And the impedance of, is like a C. Okay? And it is, and the impedance of any mass is like an inductor. Okay, so it's kind of become ms, but this is the velocity. So if you wanted to like have the output versus the movement, which is normally is going to be the variable that we wanted to like analyze in mechanical system, we just simply make another derivative. So it's going to be ms. Are we good? Everything is clear. Now that we know what are the impedances, now we can simply analyze any type of mechanical system. One example is that very simple spring damper math. We wanted to see what is the movement against the input. Are we good? Is that clear so far? The definition of the equation and the definition of the question, what the question asks us. You simply run a force analysis. One force is more input. The spring wanted to like pull back the mass, so the force is going to be backward. Same goes for the damper. Same goes for the inertia of the mass. It doesn't want to move. Are we good? Now, please think about that. I equivalent the mass, which is basically represent inertia, with L, with the inductor. What that means? That means inductor in our circuit is actually what creates inertia in our circuit. And what is inductor? The component that changes magnetic field to electrical. Relates magnetic field to electrical. Current to voltage. Are we good? So what is inertia in electrical circuit? Go deeper. No.
Yeah.
It is the inductor. But I want you to go deeper. The output is the electrical current. The output is the voltage. The input is the electrical current. This is electromagnetic field. Okay, so what we have as inertia in our electric circuit is defined by our magnetic field in the circuit. This is a parenthesis. I just want you to give kind of like intuition of what's happening in the circuit. So L gives you the circuit inertia, same as N. Now that we have all the forces, okay, again, it's like a KVL, it's a simple equation. These three added together should be equal to this one because we wanted to have a steady state. Are we good? We pull out, we adjust, we apply the force, the system did it works, and now the mass at a certain point is in a place. So on that place, the force and the system reaction should be equal to each other. This is a mechanical kind of a concept. So if this is the equation, we know how to run a Laplace transform on that. And if we have the Laplace transform and we want to find XS over FS, then it's easy. Is that clear? Any question on that? Any question? No? It is the same as electrical circuit. You just have to know what is like in the you run a KVL on electrical circuit, you run a force analysis on mechanical circuit. And what is electric KVL? KVL is the conservation of the energy. Okay, here is also conservation of the energy. Whatever you have as an input should be whatever you have as a negative force from the system. It's conservation of energy. Very good. Now, let's go to a more complicated example. You don't need to worry about when you get the complicated circuit. It's just another step similar to what you had in the simple one. Now you have 2M, okay? That means you have two X's. Do you remember that two loop circuit? Now you have two mass circuit. You have two movement, X1 and X2. So similar to previous one, now we have a vector of X's and the vector of everything, the forces and the system. Now, to find that, similar to the KVL, conservation of the voltage, we run a similar conservation of the force for each of those mass. This one is gonna be the conservation of the force for the M1. And this equation describes the conservation of the force for F2. How we find that is simple. Like, what is the forces on M? We have one F pushing. We have one K1 force. Okay. We have that damper force toward that works against the force is damper, correct? It works against our input force. We have a friction here, again, works against our force, same as K here. So this is what I mean by running K conservation of the force. So you know how to list all the force and the direction. And when you have that, you simply can have the conservation function. Are we good? The conservation equation. We have that. We already did the Laplace transform because we know how to do that. If you wanted to like consider the x2 to the f, you can find it here. Same goes for the oh, we only have one x2. So if you want an x1 and x2, it's just a vector times a g times the f, f1, f2. Please write that. This is the g. This is x1, x2. It's a simple two equation, two variable. Are we good? So simply, you can find the transfer function with the same step-by-step work that we done for that two loop KVL for these two mass mechanical system. Any question?
Typically, when we analyze, you know, do we usually analyze distance to relative to force? Do we ever look at acceleration or velocity?
If you have a distance, the derivative of that is going to be velocity, and the derivative of that is going to be acceleration. So you could have the output of the velocity, but like for example, you wanted to like have the output of velocity as actually like, okay, I'm going to ask you that question. Let's say here we have x2. Okay, we wanted to like find v2 over fs. What we should do? Similar to that current voltage of capacitor that we talked about. What we should do to find this one? What is v2 in respect to x2?
Oh, in the full distance divided by x over t.
dx over dt. Correct? What is the Laplace of that? Sx. So you multiply this one by s, you have the function for the velocity over the input. You multiply another s, you have the acceleration. Make sense?
Yeah.
Any question? Which, by the way, when you do the control system, you're gonna say when you want to like design a control system, like for example for a robot, when you have the x over input, you normally have more poles. Okay, for example, like a pole in zero. Okay, which when we are gonna talk about that, pole in zero would create a stability marginal problem for the stability. Okay, so simply by controlling the velocity instead of the location, you multiply the whole system by s, meaning you eliminate that s, the zero in denominator that happened to be on a marginal kind of like place for stability. So you have more stable system. Makes sense? We are gonna, this is kind of like a point, but we are gonna learn what I mean by that. Okay, later on when we talk about the pole and zero. Now, mechanical system is not always linear. We could have a rotational mechanical system, especially in electrical engineering. We mostly work with a rotational one, okay? And it's the same. It's just different. Instead of like an X, we have theta. We wanted to see how it rotates. What is the placement of rotation? Instead of linear placement, we have rotational placement. Are we good? So it's a simple example. Now let's find out. This is a motor. This is a DC motor. You should learn that in energy conversion. If you pass that, I don't know if you pass that or not yet. Energy conversion would teach you how to model DC motor. Okay, search on that. This is the equivalent circuit of a DC motor. Okay, so now you want the theta versus that EA, the input voltage. Basically, you want to see how the motor works based on the amount of voltage you apply to that DC motor. Make sense? Is that clear? Now, how to do that? What is the voltage across the rotor? This is a concept that you learn in energy conversion. I don't know if you passed that or not, but just take it from me. Okay, so it's gonna be the voltage across the motor is gonna be the coefficients of the motor times the derivative of the rotation. Okay, so Laplace form is KB S theta. Here we have a KVL. We run a KVL. We have armature resistance times the armature current plus the inductance of the armature. S is impedance. The inductance was SL, right? The impedance, the inductive impedance of the motor times the current plus that voltage across the motor, which is back EMF. If you wanted to like know that, it's called back EMF. When you have a rotation, you have induction in the circuit. Okay, that will resist the force. Okay, so it's a back EMF, and this is the formula for that. Now you have this. You simply replace VB here, and basically you have your transfer function. Are we good? No, I don't have enough time to go through the linearization. Let's talk about that in the next session. because I wanted to like make sure that you know how to define that. Because, as I said, most of the system that we talk about in the control system, we consider it as a linear, but that's not going to happen when you work actually out there. So you need to know how to deal with the nonlinearity in your system. Any question about what we discussed today? No? Okay. Thank you very much and have a good